Okay, so today we are doing 3 hours, and the subjects will be, in the first hour, metric. What is a metric on a manifold? The second hour, a quite difficult subject, which is the subject of connections on a manifold. That is a way to take directional derivatives of vector fields, for example. And in the third hour, I will try and explain a bit what is, I mean, not really what is in the whole, but some small parts of information geometry, which is an application of these concepts to well, information theory, in a way. Okay, so let's start. Metrics. So let's start easy. I mean, this is something you probably have studied somewhere in linear algebra or whatever. A scalar product on TPM. So TPM is a tangent space at P, so it's a real vector space. It's RK. A scalar product is a bilinear symmetric positive definite form. That is a function from TPM times TPM to R, which is bilinear, symmetric, and positive definite. Now, a bit of notation. The space of linear functions from TPM to R is denoted by TPM star, which is the cotangent space. We already talked about that. And it's usually called the dual of TPM. I mean, for a generic vector space, you won't call it cotangent, but you will just call it dual. So the dual of a vector space is the space of all linear functionals from the vector space to R. Now, if you take two covectors, so elements of the dual, alpha with P and beta with P, which are elements of TP star M, so alpha P is a linear function from the tangent space to R. Beta P is a linear function from the tangent space to R. We define their tensor product, it's called, alpha P tensor beta P, as a function from pairs of tangent vectors to R. So this function takes as input 2 tangent vectors and gives you back a number simply by multiplying them. So alpha P acts on the first entry and beta P acts on the second entry. Quite obviously, for example, this is not symmetric. This is clearly bilinear because alpha is linear and beta is linear. So whenever you if xp becomes a sum of 2 terms, alpha will become the sum of 2 terms, and they will both be multiplied by beta, so it's bilinear. It works. It's not symmetric because if you change x and y, you get alpha y times beta x, which is, I mean, there is no reason for why it should be equal to alpha x beta y. Unless alpha is equal to beta. We can take linear combinations because, I mean, the property of being bilinear is preserved by linear combination. So if we sum 2 bilinear functions, we get a bilinear function, etc. So we can define this symmetrization. So we take alpha tensor beta plus beta tensor alpha half. And this is just denoted by alpha beta. So, I mean, resembling the fact that the usual product between numbers is commutative. So alpha beta is equal to beta alpha. So alpha beta of x, y is 1/2 of alpha x beta y plus alpha y beta x, which is clearly symmetric. So in general, a bilinear form on the tangent space is a combination of terms alpha p tensor beta p. So these expressions won't give you all the bilinear forms, but if you add them up, multiply them by, you get all the bilinear forms. And then every symmetric bilinear form is a combination of terms of this kind, alpha, beta. This is called symmetric product for obvious reasons. So a scalar product is a particular element of Tp star M tensor Tp star M, which is the set of bilinear form, which this particular element is symmetric and positive definite. So by this symbol, so no. So this is not just the set of all tensor products of the elements. It's the set of all linear combinations of tensor products of the elements. So it's a set described more or less as C1, alpha 1, tensor beta 1, plus Cn, alpha n, tensor beta n, sorry, capital N, such that alpha j, beta j are in T star Pm, Cj are real numbers, well, and n is any integer. So it's a set of all possible linear combinations. And in principle, I don't know how many terms I need. Okay, so a scalar product is an element of this space because this space is the space of all bilinear forms. So a scalar product is a bilinear form which is symmetric and positive definite. As we define the tangent bundle, we can define the tensor product of the cotangent bundle with itself, which is just the set of all pairs P and B, where P is a point and B is a bilinear form on the tangent space at that point. So B is an element of Tp star M tensor Tp star M. So unraveling the notation, B is a bilinear form on the tangent space at P. So B is something which takes two tangent vectors at P as an input and gives you back a real number. Okay? At every point. So you glue everything up and you end up with a bundle. And this thing is a manifold. As we showed it for the tangent bundle, we can show it for this one. A Riemannian metric now is a smooth section, usually denoted by G, of M of the second tensor power of T star M, so T star M tensor T star M, such that, so smooth section of this thing means it's a bilinear form at every point, such that for every point and for every pair of tangent vectors, it's symmetric, so gxy is equal to gyx, and gxx is greater than 0 for all x apart from 0. So this second part is positive definite. So a Riemannian metric, in other terms, is the choice at every point of a scalar product on the tangent space. And this choice has to be a smooth choice, varying smoothly with the point on the manifold. So if you write it down as a function of the point, the scalar product, the matrix of the scalar product should be a smooth function. Now, in local coordinates, so we take a coordinate chart. We take the local coordinates x1, xk, as usual. We have the local frame for the tangent bundle on U, which is partial 1, partial k. The local coframe given by the coordinates is dx1, dxk, where dxj is the the section of the cotangent bundle, so the differential form, such that, I mean, a differential form is something which takes a vector field and gives you back a function, okay? So at each point, it takes the tangent vector and gives you back a number for each point. So you, in the end, for each point, you have a number, so you have a function. Now, we just need to tell how these elements behave on the local frame, because the local frame gives a basis of the tangent space at every point. Once we define a linear function on the basis of on a basis of the space, we define completely uniquely the linear function. So we just have to say what dxj gives you when you apply it to partial I, del I, whatever you want to call it. By definition, I mean, these differential forms are the differentials of the coordinates, which are functions from the manifold to R. So by definition, this is the partial derivative in the coordinate I of the coordinate xj. So if you derive a coordinate with respect to another coordinate, it gives you 0 if they are different and 1 if they're equal. So you get the Kronecker delta, which is 1 if the two indexes are equal and 0 otherwise. It's fairly simple linear algebra to show that at every point these elements give you a basis of the cotangent space at that point, of T star PM. So we have sections dxi tensor dxj. So you remember, if you have two elements of the cotangent space, the tensor product is the function that acts on pairs of vector fields, calculating the first element, the first vector field, times the second element, the second vector field. If you do it at every point, you get a section of the T star m tensor T star m, and quite obviously, as these guys generate T star m, all the possible tensor products, which are n squared, k squared, sorry, generate T star m tensor T star m. On U, obviously, everything is local. And if you take the symmetric products, so I will write it again, but by this symbol, we just mean 1/2 of I have to clean the, yeah. Oops. One-half of the sum of the two possible tensor products. Bear in mind, this is not a differential form, okay? A differential form is alternating. So if you exchange the two differentials, you get minus the original one. So in case you're wondering, this is not a differential form. It's the symmetric product of two differential forms, which is a symmetric bilinear form. So if you ever write a differential form, you will find things like this, which is completely, is the opposite thing, okay? So this is the symmetric product, that in white. The one in blue is the skew-symmetric product, the alternating product, which is skew-symmetric for two terms. Okay. So with respect to this basis, a metric is usually given as G equals Gij dxe tensor dxj, which is, if you do all the computations, the elements remain the same, Gij dxe symmetric product dxj, where Gij is equal to Gji because it's symmetric. With this notation, the scalar product between two vector fields is Gij, lower indexes, xi, yj. So remember, the lower indexes give you coefficients of sections of the cotangent. The upper indices give you coefficients of sections of the tangent. So the coefficients of a vector field have superscripts, coefficients of a bilinear form on the tangent space, so tensor product of sections of the cotangent have lower indices. And when an index is repeated, it's understood that you are doing a summation on that index. So this should be sum over E and J of Gij, Xi, Yj. Now, metric structure. Yes. Okay, so we take a k-dimensional manifold and a Riemannian metric. The pair manifold metric is called Riemannian manifold. Okay. Now, given a piecewise smooth curve, so I mean that it's, well, you probably all know what piecewise means, but it means that it's smooth apart from a number of points where it's supposed to be continuous anyway. And, well, some other hypotheses. I mean, smooth arcs, one joined with the other. Given a piecewise smooth curve gamma from AB to M, its length is, with respect to G, is Lg gamma, which is the integral from A to B of the norm of the tangent vector. So the norm is the norm induced by G on each TPM. So if you want to write this thing is just the square root of this thing. Notice that this is a function, okay? So we integrate it along this is a function depending on t, so the parameter on the interval, and we integrate it on the interval. If you reparameterize the curve, so if you take a diffeomorphism between two intervals, and you define gamma tilde, which is gamma composed S, this diffeomorphism, so we have a new parameter S, then the length doesn't change, okay? Because it's just a change of variable inside the integral, and so it doesn't change. Given the length of a curve, you can define a distance. So on a Riemannian manifold, you can define the distance with respect to the Riemannian metric between 2 points as the infimum of the lengths of all curves, piecewise smooth, piecewise Lipschitz, whatever you, such that they start at P and they end at Q. And this is called the Riemannian distance between P and Q. This is a distance, which means that it has three properties. The distance between a point and itself is 0, because you can take the constant curve, which has tangent vector 0 at every instant, so the integral is 0. And you cannot go below 0, because the length is the integral of a positive function, so it's greater or equal than 0. It's symmetric, so the distance between P and Q is the distance between Q and P. You just reverse the curve. And then the triangle inequality. So the distance between P and Q plus the distance between Q and R is greater or equal than the distance between P and R. Now, an example which I don't. Take R2 minus the origin, which is our manifold M, which has local coordinates x and y. So there are global frame, which is d partial 1 and partial 2, and the global coframe, which is dx1 and dx2. And you define a metric G, which is sorry, the 1 should be above. Yeah, sorry, x and y is not x1 and x2. So Gij is just delta ij, so it's the identity metric. So this is the Euclidean metric, okay? Now, so you basically have the plane where you removed the origin, okay? Now, suppose you want to go from P to Q, which are such that the line between P and Q meets the origin. Now, the distance between P and Q will be just the Euclidean distance in R2 from P to Q, but there is no, the infimum is really an infimum, so it's not a minimum. So in M, nope. There is no curve. Gamma with gamma 0 equal P, gamma 1 equal Q, and length of gamma equal their distance. Obviously, because every curve has to go around a bit the origin, and so you never have the proper distance between P and Q. Maybe we will talk. We will almost surely talk more about this later on, but for now, just an observation. Okay, now some random concepts which are worthy of being mentioned now. Localizometries. If you have two Riemannian manifolds, so M with the metric G and N with the metric H, a function, a smooth function from M to N is called a localizometry if the map given by the differential, so the differential of f at P from the tangent at P of M, the tangent at f of P on N of M, is an isometry between Euclidean spaces. So TPM as a scalar product, GP, TFPN as a scalar product, HP, and you want that DF at P is an isometry. So it sends an orthonormal basis to an orthonormal basis. So if you take an orthonormal basis for GP and an orthonormal basis for HP, the matrix of DFP is an orthogonal matrix, whatever you want. Obviously, this means that M and N have the same dimension. If the map F is a diffeomorphism, then it's called a global isometry. And it's an isometry between the two distance spaces. So if you take 2 points of M and you look at the images, the distance in M is equal to the distance in N. In general, you can define the pullback metric because a metric is a section of T star M, tensor T star M. You can pull back the sections of T star M, so you can pull back also the sections of a tensor power easily, like this. So the pullback of the metric H, which is on N, is the metric on M, which acts like this. It takes two vectors tangent to M, it pushes them forward to vectors tangent to N, and takes the scalar product with respect to H. So F is a local isometry if the pullback of the metric on N is the metric on M. Obviously, for a map being an isometry, it depends on the matrix you choose. And you can choose a lot of metrics on a manifold. For example, we take the same M as before. We and we define let's see. Okay, we can give a metric by giving an orthonormal basis. So if I give you an orthonormal basis, you can write down the metric, because in that basis the metric is represented by the identity matrix. So let's say our orthonormal basis is Y1. Why Y1? So these are two vector fields. By the way, they are orthogonal also for the Riemannian metrics, so we know that they are independent at every point. And because the Riemannian metric is just the Euclidean metric, because the Euclidean metric is just the metric for which partial 1, partial 2 is an orthonormal basis. So the scalar product with respect to the Euclidean metric is just x1 times minus x2 plus x2 times x1, which is 0 at every point. Okay? These are independent because 0, 0 is never I mean, you never set both variables to 0. And but they are not an orthonormal basis for the Euclidean metric. So we define. I have to clean the screen of this thing. So we define G such that, let's call it U, is an orthonormal frame. So the word frame means that it's a basis at every point. It's a set of sections which give a basis at every point. Now, with this metric, M is is not isometric to the previous M, which is with the Euclidean metric, because it cannot be. This is an orthonormal basis here, but not there. So the identity function wouldn't have an orthogonal matrix. This is actually a cylinder, so it's isometric to a cylinder in R3. So it's like you're opening up the origin and you are closing up the infinity and you get a cylinder. You can try and write down a cylinder in R3 with the metric, the Euclidean metric of R3. But in particular, this is not isometric or even locally isometric to the previous one. Okay? So this is a concept that depends on the metric, not only on the manifold. So embedded submanifold, just because I talked about the thing. So if you have an immersion that is a smooth map which has a differential which is injective at every point, and E of M is a submanifold of M bar. So for example, think M bar being Rn. E is called an embedding. Suppose that you have G bar, which is a Riemannian metric on M bar, so the big space as the Riemannian metric. You can pull back via the via I, the global metric restricted to M, and this is called induced metric. Now M with the pullback metric is a Riemannian submanifold of M bar, of the big space. What does it mean? It means that you take two tangent vectors on the submanifold. There are also two tangent vectors in the big in the tangent of the big space, and you take the scalar product inside the tangent of the big space, and that is the scalar product also in the tangent space of the submanifold. So you are restricting the bilinear form, which acts on the whole tangent space of Rn, for example, to the tangent space of just a submanifold. A curve on M, the length of a curve on M will be the same if you compute it in the submanifold or in the ambient manifold. So if you take the sphere in Rn and you take the induced metric by Rn on the sphere, which is called the round metric because it's round, the length of any curve there is the length of a curve inside Rn, but the distances are different. Well, take the sphere, take the north pole and the south pole. The distance in Rn is twice the radius. The distance on the sphere is bigger, is half a circle. Now, the other reason for having a metric. So one reason for having a metric is having distances, computing lengths. The other reason is what is called musical isomorphism. I know it's a weird name, but take a vector field and the Riemannian metric. You can define the one form x flat, that's why it's called musical isomorphism, by x flat. A one form is something that acts on vector fields. So it takes vector fields and gives you back functions. So x flat of y is just a scalar product between x and y, g of x and y. In a vector space with in Rn with the standard scalar product, this is the transpose operation, the one that sends a column vector in a row vector. But in general, the matrix of the metric will not be the identity, so it will not be enough to take the transpose. In coordinates, this happens. So x flat is the differential form whose coefficient is the coefficient of the vector field times gij, and you see that I is repeated, so we are doing a sum over I. This is called lowering the index, or contraction of G with X, but lowering the index. So Gij multiplied by something which has an index I above lowers the index. So every time we, and these, usually you just write that xy, where is it? Xi is equal to xj gij. Again, there is a summation over j, which is meant but not written. So the coefficients of x flat, which is a one form, are these sums of coefficients of x times the metric g. And because it lowers an index, it's called flat, because, you know, a flat means to lower the tone by a semitone, actually, a note. So we have a map which is flat from the tangent bundle to the cotangent bundle, which is an isomorphism of bundles. Why an isomorphism? Well, because G is positive definite, so as a if you write down the coefficients of G in a matrix, it doesn't have a kernel. Or better, if you take a local frame and the dual coframe, and you write the matrix of the flat isomorphism, the matrix of flat isomorphism is given by the numbers Gij, and the determinant is the determinant of the bilinear form. I'm skipping a bit of details, but it's okay. The dual metric. Now, we can put a metric also on T star, which is denoted by G to the -1, or sometimes G star, it depends. I mean, it's not a standard notation, and you will see in a moment why. How you define it? Well, you define it this way. So it has to be compatible with the flat isomorphism. So if you take two vector fields and you produce the corresponding differential forms, so you x and y, and you make x flat and y flat, so you lower the indices, you get two elements of the cotangent bundle, two sections of the cotangent bundle. The inverse metric on those two sections should be the original metric on the two vector fields. So G to the -1 of x flat, y flat is G of xy. This is called the dual metric, and well, this part, I don't know if you ever, but anyway, forms act on vector fields, but the other way around, vector fields act on forms. So the linear functions on the cotangent are given by the elements of the tangent. So a metric on T star Pm is a section of Tm tensor Tm, same as before. So it's a symmetric section, therefore we write a symmetric product between sections of Tm, which are partial I and partial j, and we write g to the minus 1 as gij, but upper indices, partial I, partial j. gij is the ej element of the matrix, gij lower indices is minus 1. So this is why it's called the inverse metric. The matrix of the metric on the cotangent is the inverse of the matrix of the metric on the tangent. So gij above is the element ij of the inverse of the matrix gij lower indices. Written with the Einstein summation, gij gjk is delta ik. So if you think of it, this is the product between two matrices. And this is telling you that the product has ones where row and column are the same and zero where they're different. So it's an identity. So you're writing that these matrices are one the inverse of the other. Now the sharp isomorphism is a very stupid thing. It's the inverse map. Okay? So you have x goes to x flat, and you have the sharp isomorphism, which is induced by the inverse or dual metric, and is again, the inverse metric is again symmetric and positive definite, you can prove it. And so alpha, if alpha is a differential form, alpha sharp, so you are raising an index, is alpha I gij. It works the same way, just you are transferring an index from lower to upper position. If you do x, the sharp of x flat, you get x again, and that's exactly because gij above, gjk below is delta ik. So this gives you a way to take a form and write down a vector field. Okay. You could say, okay, but who cares? I mean, I can just take the coefficients of the form and use them as coefficients of a vector field. True in a local frame. When you change coordinates, these things will change in a completely different way. So if you have if you remember the picture, if you have two coordinate patches, two coordinate charts, you can do everything on here because you have a local frame and coframe. You can do everything on here because you have a local frame and coframe, but on the intersections, the two operations you do, just taking the coefficients and using them for another thing, won't coincide. So you take the same, for example, differential form, and on this coordinate, on one coordinate chart, you use its coefficients so that in that coordinate chart to produce a vector field. You do the same on the other coordinate chart. The differential form is the same one, is 1, is defined all over M, but the vector field you obtain is not. Whereas alpha sharp is defined coherently all over M, because we are writing it down with the coordinates, but alpha sharp, which is a vector field, so it acts on functions, on the function f, which is the same as, by definition, df acting on the field alpha sharp, is actually the inverse metric applied to df and alpha. So you see, it's a completely intrinsic. We are not using coordinates. We're writing things down in coordinates because then it's useful. But we are just doing things with global objects. So alpha sharp is something which is defined all over M. We don't have problems that in this coordinate, in those coordinates, it's an object, it's a true geometric object. Okay, so why are we doing all this? Because we can do the gradient of a function. Okay, this line was already 4 or 5 slides ago. If you take a Riemannian manifold and the function smooth from M to R, the gradient of F is the vector field grad F, or nabla F, which is df, the differential, sharp. So with respect to a local frame, grad F is Gij partial IF dj. So it's not the vector of the partial derivatives, because if you change coordinates, the partial derivatives change wildly. It's the inverse metric applied to the vector of the partial derivatives with respect to any coordinates. And this gives you a coherent thing which is defined all over M. If you remember, go back to lecture 2, what we did there was defining the gradient as via the Reed's representation theorem. The Reed's representation theorem tells you exactly that a scalar product gives you an isomorphism, which is the flat isomorphism in this case, between the linear functionals on a space and the space. So the dual and the space. So when we started in Rn, we did the same exact thing. We used the scalar product, which in Rn is the Euclidean one, to pass from a differential to a vector field. We didn't notice it because all the matrices, Gij, upper, lower, whatever, were the identity. So it didn't matter. But in a general manifold, it matters. Now, obviously, if you have the gradient of a function, you just need to define a retraction, and then you can do the whole game of Riemannian gradient descent all over again. Now, for the first hour is enough.